Now let's talk about nuclear density. And as we all understand, that density is basically mass by volume. So let us try to have an approximate idea of nuclear density and try to see what is the nature of this nuclear density that we have. So if I have to define this nuclear density, what it means is mass per unit volume. This is what can we define as nuclear density. If I take its symbol as say rho, so this rho will be it will be mass of the nucleus and divide by the volume of this nucleus. Now, if I have to go with the mass of the nucleus, that will certainly be the mass of protons, or let's take some average value. Say mass of protons times the mass number, and A is the mass number, and divide by volume of the nucleus. So that should be the case, volume of the nucleus. And the and the mass of neutron that we have, we would like to take it in terms of atomic mass units. That will be the right thing, because that's close to the mass of neutron and proton, for the sake of simplicity here. So it will be 1.66 into 10 to the power of minus 27 times the mass number, divided by what I have is the volume of the nucleus. So this is the density. All right. Now, if I have to write down the volume of the nucleus, what will be that? So for volume, I have V, that is 4 by 3 pi r cube. But for this r, this has already been calculated from where we calculated the average size of a nucleus. This r has a relation. So this V is 4 by 3 pi. What's the relation? It is r equals r naught, a to the power of 1 by 3. So is the case I can use here r naught cube a to the power of cube by 3. So what will be volume here will be 4 by 3 pi r naught cube a. So from here, I can calculate the density of the nucleus. So density is 1.66 times 10 to the power of minus 27 by the volume, that is 4 by 3 pi r naught cube times a. And here we have a also. This a and a is going to cancel, and what we always see is a number. It is 1.66 into 10 to the power of minus 27 divided by 4 by 3 pi. Pi is 3.14 times, r naught is 1.2 whole cube into 10 to the power of minus 15 whole cube. So this will be kilogram per meter cube. And what is so evident here is that the density of the nucleus is independent of the mass number. So I can say here that all the nucleuses that we have, on an average, their average densities are same. They have the same density, and that could be understood from this equation that we have obtained here. So when we calculate this, density comes out to be 2.38 10 to the power of 17 kilogram per meter cube. So this is the density of the nucleus. So what we see here is that the nuclear density is a constant, simply a constant, and is independent of mass number of the nucleus. And if I have to correlate this density of the nucleus with the density of the Earth, then I can say you that the density of nucleus is more than Earth's density. If I take Earth as a reference here, Earth's density by 10 to the power of 13 times. And the mass of Earth is close to 10 to the power of 4. The density of the Earth is 10 to the power of 10 to the power of 4 kilogram per meter cube. So this nuclear density is very large, and it is on an average it is same for all nucleuses, because we don't find any dependence of this density on the mass number. Now, if we take an example of iron here, say, suppose I'll take an example of iron, and this iron has the density, nuclear density, that is 2.29 times 10 to the power of 17 kilogram per meter cube. And the mass of this iron nucleus is nearly 55.85 atomic mass units. Then what I'm trying to calculate is the volume. I want to see the volume of this nucleus, and hence I want to calculate the mass number. These are the two things that I want to calculate. So for that, I have the density of the nucleus that can be written as mass of nucleus divided by volume of nucleus. So I can take volume up, because volume of nucleus will be mass of nucleus divided by density of nucleus. So here I have the mass. How much is that? That is 55.85 atomic mass units. And I can convert this atomic mass unit into the kilograms, and then we have 2.229 times 10 to the power of 17. The density that is given for this nucleus, and from here I can calculate the mass. So what will be I can calculate the volume, and this volume will be 55.85 times 1.66 into 10 to the power of minus 27 kilograms divided by 2.29 times 10 to the power of 17 kilogram per meter cube. And when we calculate this nearly comes out to be 4.08048 times 10 to the power of minus 43 meter cube. Okay, we can see that we have got some minute thing at the center of this nucleus, and now I can talk about the mass number of this nucleus, because I have a relation for volume, and that volume is what, 4 by 3 pi r cube. For r I will write r naught cube, then I have a cube, so it will be a, because it's 1 by 3 because r is equal to r naught a raised power 1 by 3. So when you are cubing it, you are cancelling this 3 and 3, and finally what we do, we substitute all the values, and what we have 4 times this is 3 times v by 4 pi r naught cube. And when we substitute the values here, that is 3 times volume of the nucleus, which is 4 times 10 to the power of minus 43, nearly, divide by 4 times 3.14 times 1.2 10 to the power of minus 15 whole cube. This is going to give us nearly the value close to 56. So the mass number of iron comes out to be 56.